Our first talk is by Mert, and he's going to talk about computational polarization and straggler resilient serverless optimization. Thanks, Mert.
Hi, everyone. Let me share my screen. Okay. So thank you so much for organizing this, and thank you all for joining in these difficult times. I'll be talking about error correcting codes for distributed optimization and computations. So as you're all aware, we have this big data problem. Every day we create so many billion gigabytes of data, and the data grows faster than the world economy. And we have seen the impact of having very large data sets. We witnessed the deep learning revolution. Essentially, these are black box, very complex models. We don't exactly know how they work, and then when they work better than simple prediction models. In machine learning and data science, it's very clear more data results in better, more accurate models and better predictions. And they give rise to large-scale distributed computing problems, such as the ones in deep neural networks. But these complex models, although they can increase accuracy, they're black boxes. It's very hard to interpret what the model is actually doing. So it is actually a better practice to explore simple to complex models. And we would like to do this inexpensively. So to address this question, our approach is using serverless systems, which I'll define in a second, with error correction to auto-scale computations. So we will consider a distributed computation setting where we transmit local data sets to different workers, and we have lots of workers. So recently, there was very interesting line of work in applying error correcting codes to distributed matrix multiplication and related problems. This one is from Lee et al. 2017. So here the task is to multiply a matrix with a vector or some other matrix B, and then typically you can split the matrix A into submatrices A1, A2, A3, A4, and then distribute these to workers. And normally they will multiply these smaller submatrices with B and then send the result to a master. So the error correcting code way of doing this is very interesting. So you will use one worker and you will compute a linear combination of these data matrices, and then this will be multiplied with B. Now we have this extra redundancy. It's a redundant computation. So if one worker's result is not available, if it's late, or if there's some sort of an error, we can use the others to reconstruct the computation, right? So this will tolerate up to one error. And in this context, these are called stragglers. If there's one late computation, we can just ignore that. So any 3 out of these 4 workers will suffice in computing A times B. So I'll talk about serverless systems. This is a new paradigm in distributed computing. These are extremely low cost systems. There's no upfront investment. You just pay per millisecond, but you just have very short duration for your computations and very small, moderate computational resources. In particular, there is this PyRen package. You can run Python functions on serverless systems on Amazon Lambda. Other cloud services like Google, Microsoft Azure, they also provide these systems. These are stateless, meaning that there is no file system access. Any state should be stored in some storage service. And ideally, they should be very, very small, independent computational tasks. But the nice thing is that these are very scalable, very cheap. We can call 10,000, 20,000 workers. But there is a big problem. If you look at the return times, you will see a very significant tail latency. So if you look at compute latency and the number of workers, this is a histogram, you will see that a significant portion of the computations, they arrive very late. Some small portion, some small ratio here arrives in less than 20 seconds, but to get all your computations, you have to wait more than a minute. And this is called the straggler problem. We will use polar codes to address this. Our work is inspired by polar codes. Polar codes were invented by Erdal Erkan in 2009. These are the first constructions of codes with explicit construction. They probably achieve the channel capacity for any symmetric discrete memoryless channel. In fact, they will be used in 5G radio standard in the control channel along with the LDPC codes. So, and the theory behind polar codes is very interesting. So it's now standard in information theory and coding theory courses. They combine communication channels recursively, and they obtain better and worse channels recursively. And then in this way, they achieve capacity. So here is a very quick slide on the inner workings of a polar code. So you get a communication channel, W. This is a binary input channel, like an erasure channel or a binary symmetric channel. So you apply this transformation on Boolean inputs. And then you combine these two communication channels and you get two different transform channels. And then you extend this recursively to 4x4, 16x16 constructions. What happens is that the transform channels get better and worse. And when you do this recursively, you get a set of very good channels and a very bad channels. And then in the end, you only use the good channels. And in information theory, this is calculated with respect to mutual information. When you use the channels with good mutual information, you actually achieve capacity. So we will use the combination idea in polar codes to come up with computational versions of polar codes. And we call this computational polarization. So we have some data A, this is a data matrix, and we have a worker like an Amazon Lambda serverless system worker. This is very local, it can only tolerate small computation. And then it outputs the computation, which is f of A, some function applied on A. You can imagine this being some machine learning model, some linear algebra operation. In optimization, this can be some gradient or Hessian computation locally. So when you have two workers, you can give them two different data sets, right? Partitions of an original data set. And then normally they would compute f of A1 and f of A2, right? So the idea behind computational polar codes is using a transformation like this. This is a 2x2 Hadamard transform applied to matrices. Here we add and subtract. This is the familiar butterfly block in fast Fourier transform, Hadamard transform, and wavelet transforms. And then we transmit these transformed blocks to the workers. And then they compute the function on these local transform data, f of A1 plus A2, f of A1 minus A2. Okay. And then we have a very special decoding mechanism. This is also inspired by polar codes, although it works over reals. So we will first decode f of A1, the function evaluated on the first local data set. To do this, you actually need to wait for both of these workers. And then we assume that the workers have some random variable computation times. Here it's T1 and T2. So to get f of A1, you had to wait for both of them. So you can compute it in max of T1 comma T2 time, right? And you can get f of A1. Here we are assuming that the function is linear. And when I have f of A1 plus A2, f of A1 minus A2, I can decode f of A1 by just solving a linear system. Next, assume that you have f of A1 available somehow, okay? And now I can use either worker 1 or worker 2 to get f of A2, right? And then this can happen in minimum of T1 and T2 at time min T1, T2. So what you see here is an interesting transformation. So the worker runtimes T1 and T2, they get transformed to the maximum and minimum, right? And then the idea is to apply this procedure recursively. If you look at the runtimes here, this is the probability density of a worker return distribution. Let's say it's uniform. It gets transformed to the maximum and the minimum. And if you have two independent uniforms, if you calculate the maximum, it does have a triangular distribution skewed towards the right, and the minimum is skewed, and also triangular, it's skewed towards the left, right? And then precisely, it's this T1, T2 to maximum and minimum mapping. It's a 2x2 to 2x2 mapping. We can extend this to 4x4, very similar to the fast Fourier transform way of combining these blocks. we have these two identical blocks, and then we use two more, these 2x2 Hadamard matrices to combine it into a 4x4 block. And then we input these to the workers, right? Now what happens is that we get the max and min in the first block, and then you compute another max and another min on these variables. So you get maxes of maxes and minimums of maxes, maxes of minimums and minimums of minimums. Now this is a 4x4 transformation. So we call this a computational polarization process. It is actually a functional martingale in a Hilbert space. It is like a random walk. You start with a function, and then there's a functional mapping. It follows this rule with a certain probability. It gets squared. It's actually probability 1/2, and with probability 1/2, it gets mapped to this value. And then this is a martingale. If you average these two functions, it is identical to the original function. And then we have a theorem on convergence. If you iterate this, these functions in L2 norm, they will converge, and the rate of convergence is some exponential. It's very similar to the convergence rate to capacity in polar codes. And in particular, these functions, these are the cumulative density functions of the runtimes. They converge to unit step functions, which means that the runtime distributions, they converge to Dirac measure. They converge to Dirac delta functions. And here's an illustration. So if this is the original runtime, my workers are uniform, the computation times are uniform between 0 and 1. At the first step, they will be triangular, and then the average will be equal to the original probability density function. And then from these two, we will create two more by extending the construction to 4x4. And then this is a martingale. The sum of these two is equal to this, and then the sum of these two is equal to this. And if you iterate this infinitely many times, these functions, they get spiky and spiky, and then they converge to Dirac delta. And then how do we use this as an error correction scheme? It's actually very simple. We just find the undesirable ones, undesirable runtimes, and then we fix the inputs to 0. Essentially, you just transmit 0 matrix, but in practice, you actually don't do anything because it's all 0, so you don't compute that branch. It means that you actually cancel this bad-looking runtime, right, which is skewed towards the right, and then you're left with the better-looking ones. So your system will run in these much nicer distributed runtimes. And here's a cartoonish description of this process. We have mediocre workers. These are not very fast, not very slow, right? When we apply this 2x2 transformation in computational polarization, we get a fast worker and a slow worker. And if you combine two of these fast workers, you get something even faster, like a GPU, and then some of the slower ones. And then you can freeze the slower ones to 0 and not use them. Effectively, it makes the system runs faster.
Mert, I have a quick question. Maybe it's a conceptual question that I'm struggling with. So here you have like things going in series and things going in parallel. So how do you avoid not things having to wait for the other people to give them the input to process, or this?
Okay. Yeah, so that's a very good question. So when you freeze a worker, like here, right? So the decoder runs successively, right? First, it tries to decode the function evaluated at A1, and then A2, and then at A3, and then at A4, right? So if you can evaluate f of A1, you can, right? If you can't, we will freeze it to 0. So whatever you need at a certain point, it is either computed or frozen to 0.
Okay. Yeah.
But you're right that there's that uncertainty. It works fine because of this special
because I'm assuming you're gonna go deeper into this, right?
Yeah.
And this wouldn't be a problem for the 3rd stage and 4th stage.
No, if you follow this order, it won't be a problem.
Okay.
And then the same order arises in polar codes. There is a very specific sequence that you should do decoding. If you do that, there won't be any problem.
Okay.
Yeah. Okay, and then here's how the system looks like. So we have some encoding step, which is that butterfly transformation on the data matrix. And then we put everything to a storage service like Amazon S3. And then we call these Lambda functions. And then we do decoding locally. This is how the distributed computing system will look like. And we can compare this with other coding methods. And recently, lots of different methods for distributed matrix multiplication and other linear algebra operations have been proposed. So there are Reed-Muller codes, LT, Libby transform codes, LDPC codes, faster Reed-Solomon codes based on fast transforms. So computational polar codes here have an advantage because they have super cheap encoding and decoding complexity. Encoding and decoding, it doesn't involve any matrix or number multiplication. It only uses addition or subtraction. And because of this, it can scale to thousands, 10,000, 20,000 workers. And here's a comparison between Reed-Solomon codes and polar codes in encoding complexity. Green curve is the polar code encoding. And then if you encode Reed-Solomon codes naively, you will get the blue curve, which is cubic in dimension. You can make that faster with the Fermat numbered transform, but it's still slow compared to the polar codes. And then in decoding time, there's even a larger gap because the decoding operation in Reed-Solomon codes is very slow, and it doesn't get better with the fast numbered transforms. And here is a histogram of compute times on Amazon Lambda. This is real data. And then when we apply our computational polarization scheme, we get this much better runtime because we freeze lots of computation paths to 0. And then by fixing them to 0, we adjust the rate. Here we are using 1,000 redundant workers and a total of 1,500 workers. Okay, so the rate is 1/3. And this is why we get this very favorable runtime distribution. And then we can use this in optimization for least squares models, generalized linear models, such as logistic regression, support vector machine. The computation usually boils down to matrix vector products that look like AX and A transpose Y. And then we apply the coding and decoding mechanism. And then here is time versus objective value in random data. And as we increase, as we decrease the rate, the convergence actually improves because we get rid of the stragglers. And on the right, you see the ImageNet data. This is a very simple logistic regression problem on ImageNet. And then this data set is very large. We have to use distributed workers. And when we use 128 workers, we get these blue points in convergence. And when we decrease the rate to 1/2, we get the orange curve. It's definitely faster as we decrease the rate. So this can be done for linear functions of data or polynomials. It will boil down to same computations. It can also be applied to gradient and Hessian calculations involving the data matrix. I have a very short example on this. So in zeroth order methods, we actually don't have access to gradients. We only have access to function values, and we can estimate gradients. If you have a function f of x, the gradient with respect to xi can be approximated via a finite difference approximation. Here, e sub I is the ordinary basis vector. And we can come up with a coded version of this. Instead of the ordinary basis vectors, we perturb the function in arbitrary directions. And then this essentially measures the inner product of the true gradient vector with these direction zi's, right? And then if we choose these zi directions using the coding matrix we introduced, the decoding problem is essentially a linear computation problem. We can decode the gradient from these function differences. And then here's an application of this to adversarial examples. Given a trained neural network, finding adversarial examples is a constraint optimization problem. We have an image x0, and we would like to find the closest image in some norm, which is classified in a wrong class. Here, the probability of being classified to J is greater than the true probability of being in class I. This is a constraint. And then this way we can find a nearby example which is classified wrong. And we compare the training cost versus time in CFAR10. Here, this is an airplane. It's classified as a truck. And then in finding this example, we're solving this optimization problem using the coded gradient estimator. And then when we do the computational polarization, we get the red curve in convergence. This is done on Amazon Lambda as well. And we are comparing it with finite differences, FD, which is the usual way of approximating gradients perturbing the function in ordinary basis directions. And then it's also comparing it with structured evolution. This is a novel idea. It uses Hadamard matrices, and then it is a random search method. Because we utilize redundancy, we get rid of the stragglers, and then we get a much better convergence time trade-off. So some conclusions and future work ideas. So this is a scalable and error-resilient method. The encoding and decoding is very cheap. This is the most important aspect. It can be done for least squares and generalized linear models. So one thing we're trying to come up with is privacy enforcing and encrypted ways of distributing data. It looks like this can be done with a clever choice of coding matrix. And we are also trying to extend this to more general convex optimization problems. For instance, problems with constraints, non-convex optimization problems. And we are actually trying to extend it to neural network problems. And we develop convex optimization convex optimization approaches for these neural networks. And this is something we are currently working on. And here's a related paper on this. Exact convex optimization formulations for neural networks. So that's all. Thank you very much for your attention. If you have any questions, I'd be very happy to answer.
Thanks a lot, Mert. So I think we have time for one question.
Can I ask a question? This is Gauri.
Of course, yeah.
Hi, Mert. Really nice talk. A quick question. You said that these codes are comparable with rateless LT codes. Could you comment on how the runtime compares? I see that the encoding and decoding complexity is the same as LT codes.
So yes, you're right. In LT code, you also get linear time encoding and decoding. Yeah. In our comparisons, however, the error in LT codes, they were much higher because of the randomness in their construction. You're right that they're also fast in encoding and decoding, but the performance is, I believe, it's worse.
Okay, thank you.
Thank you.
I also have like a very quick question. So when you compare this ImageNet data, you show a plot where you are comparing with uncoded with 128 workers versus coded with 256 workers. Yes, right, this one. So wouldn't it be a fair comparison to also do uncoded with 256 workers, because you have that much of redundancy, and then see what would be the time?
Oh, yeah, I see. Yeah, you're right. You're absolutely right. If we had 256 workers and no coding, we could have partitioned the data more finely, right?
Right.
Yeah, you're absolutely right. But we didn't do that primarily because in ImageNet, it's distributed over classes where every worker reads just one file and every class file is stored in that. So it's because of the data granularity. But you're absolutely right. If we are free to divide the data any way we like, that would be a much better, fair comparison. You're right.
Right. So one thing is that I'm trying to do is to take this thing in practice. And I work a lot with this AWS tools. And it seems like there is some ad hoc stuff that are already being done to tackle this straggler thing. And like, if we want to use sophisticated coding things, it's like, yeah, it's like a hard sell. And one of these things is this, like, if we, but I understand your answer. Yeah, makes sense.
Yeah, I see. So I think the simplest way to deal with stragglers is just replicating, right?
For one thing, yes, like that.
So it has to be
or
really
maybe
low
just neglect that thing, right? So if it is a straggler, you just don't, like, for example, we sometimes just don't deal with that at all. We don't wait for it, and whatever we get, we just do it, proceed with the iteration with that data. Does that make sense?
Right, exactly. That's another approach. Like in stochastic gradient descent, you don't need to calculate the gradient. Only a subset would be basically work.
Exactly.
Right, but I don't think it's clear which one is best if you wait for all, do coding, and then do exact gradient descent. So in our simulations, when you're solving convex optimization problems, in Newton's method, for instance, calculating the exact gradient is very important, because if you don't, the algorithm might diverge. In training logistic regression, the algorithm can tolerate noise because it's a simple linear model. I think in those, you can ignore the stragglers.
Can I make a quick comment? For SGD, actually, if you ignore the slow gradients, then we can prove that that is better than doing coding, because the you'll just.
Gauri, is this the slow and still gradient paper?
No, that is with asynchrony. Here, if you're ignoring slow gradients, then it is just as if you have a smaller effective mini batch size if you're doing synchronous gradient aggregation. And for that case, with some simple back of the envelope calculations, you can show that it is actually better to ignore slow gradients. But that said, if say the data is heterogeneously distributed across the workers, then it may not be okay to ignore gradients from some worker that is consistently slow.
Gauri, you also need to guarantee that somehow the stragglers are independent over time, right? You need that assumption also, right? Meaning.
Yes, yeah, that's what
So on average, you see all the data points along the optimization somehow.
Yeah, that's true.
Okay, thanks a lot, Mert.